amygdala is part of the emotion processing network. It's part of a very intricate network. And also in a number of psychiatric disorders, amygdala dysfunction have been observed. And for example, amygdala hypoactivity or hyperactivity is actually associated with the symptom anxiety that is often found in anxiety disorders, or also hypoactivity, too little activation to previously rewarding stimuli associated with anhedonia. So there have been studies already showing that patients, like here in this case with major depressive disorders, are able to learn to regulate their amygdala activity using real-time neurofeedback. So for example, here in this context, it has been shown that they are able to up or down regulate their amygdala. So what we are doing in real-time neurofeedback, traditionally in fMRI, we assume that the stimulus with a certain stimulus intensity is actually parametrically modulating the target region. So we can also instruct a subject to do some sort of regulation. So internal processes are actually counteracting or even increasing these effects that the stimulus is doing to this region. So in real-time neurofeedback, we actually make use of an online processing of the data. And if we instruct subjects to up or down regulate a target region, we can provide this as a feedback to them that facilitates better regulation of the target region. So what we do in closed-loop neurofeedback, we actually combine this symbolic representation of neurofeedback and the target stimulus. So in this case, emotional phases. So if they have to upregulate, let's say, the amygdala, they are actually also upregulating the stimulus that they are seeing. So in other words, one can say that by instructing the subjects to regulate the faces, like making the faces more happy, they drive the amygdala with a different intensity, with a different perturbation, which then also changes the stimulus intensity, which again can be used as an objective feedback for them to see how their regulation mechanisms are working. So we assume that this closed loop feedback is actually more, provides a better validity. It has it is a naturalistic stimulus, so when you think of social anxiety disorders, patients who have problems with coping with emotional phases, it actually helps them to be exposed to them. There are no distractions, so you don't have this dual task interference, so when they're actually about to do something effective, appreciating the stimuli they are seeing, they're not distracted by some cognitive task of understanding the feedback. And we can also use stimuli that can be more rewarding, like this social reward, for example. Additionally, it also would allow for more complex designs, so taking ideas from control theory and inspire our simulation models based on that. The software we're using for real-time neurofeedback was OpenNFT. I very much encourage you to use the software. It's open source and it's MATLAB based, so there's SPM running in the background. So essentially all you know from offline analysis is also happening there in real time, but at a processing time of 0.4 seconds on an average, quite good personal computer, but you don't need any special equipment for it. So in our case, we optimized our field of view to cover the amygdala, also the temporal pole, because I also agree that it's interesting. Also orbitofrontal cortex, so we optimized for a high temporal resolution of 1 second and a high in-plane resolution. Each block consisted of 20 seconds baseline and 40 seconds emotion regulation, and this happened all within one training session of 4 different blocks. So we had 2 different groups. Their instruction was to up or down regulate the amygdala, so that is make the faces happy, 16 subjects in the happy up group, or down regulate the amygdala, make those fearful faces less fearful. What we did observe was a slight upregulation in the happy up group over the 4 runs within 1 session. Remember, this is, even though it's a training study, it all happened within 1 hour. And in the fear down group, they were able to down regulate the amygdala. So what we observed as immediate effects were mood changes. So we did the PANAS, and in the happy up group, we saw a slight increase in PANAS positive scores, a slight decrease in negative scores, and a slight decrease in STS. In the fear down group, importantly, we observed a significant decrease in the PANAS negative scores. And please remember, those were healthy subjects, so you wouldn't expect any large changes, actually. Interestingly, this post-pre difference in the PANAS negative score correlated with the cognitive reappraisal dimension of the emotion regulation questionnaire and the noticing dimension of Maya. So are there any long-term effects? So we had 6 subjects coming back to us for a second scanning session. And here in this fear down group, you can see that they actually started on the same level they finished 2 weeks earlier when they were here. Additionally, there are also changes in affective connectivity. Our target regions were the visual cortex, the FFA, the amygdala, and the orbitofrontal cortex. And in our model, we assumed that the task regressor was entering as a driving input the visual cortex, and from there the signal propagated to FFA, amygdala, and OFC. There were also bidirectional connections between prefrontal cortex and FFA. And what we observed in the first run in the happy up group was this upregulation of the amygdala by FFA and orbitofrontal cortex, and an upregulation by FFA to amygdala in the fear down group, and a strong down activation by the orbitofrontal cortex. So this is actually something that you would expect from emotion regulation when people try to down-regulate their amygdala. This is something that we have found in previous studies already, also with social anxiety disorders, that it's missing there, for example. So the interesting thing that happened over the course of the training is when we looked at the other runs, we saw in the happy up group an overall positive activation of the amygdala by OFC and FFA. In the fear down group, we actually saw a decrease of FFA input to the amygdala. And this negative regulation by orbitofrontal cortex to amygdala was actually also gone. So we see a difference between the first and second run. This could be some kind of learning mechanism. Then overall, in the third and fourth run, we see no significant input from orbitofrontal cortex. So this could be actually some kind of mechanism where the input from FFA is decreasing, so there could be some local regulation happening in the amygdala and no explicit regulation where the orbitofrontal cortex is needed anymore to downregulate the amygdala response to the emotional intensity. So what are our advantages of closed-loop neurofeedback? We assume it's ecologically more valid, it's more motivating, and there is no task interference, no dual task interference. So the next step would be to apply this in a clinical setting. I'm working at a psychiatric hospital after all, so next step would be to include this patients with major depressive disorder or social anxiety disorder in our study. And what we found here especially was the downregulation of fearful faces worked in healthy subjects by decreasing the negative mood, and it also changes affective connectivity. There are today 2 more chances to see me at my posts. I would be very happy to ask questions there. I also have some more information on 2 additional groups. So we also did what's called a negative closed loop, where there's actually an indirect relationship between the stimulus intensity and the amygdala signal. Yeah, you would have time to also discuss the technical details of doing real-time neurofeedback. I would like to thank our group leader, Frank Janowski, Amelie Haug, and Nada Frey for helping me with the acquisitions, and would be very happy to answer some questions. Thank you.